Hi everyone, welcome back to the second lecture of Respiratory. We're going to start learning today about how the lungs work, how we breathe, and what actually causes that movement of air in and out of our lungs. So, as always, let's start with our not really attendance questions. First, explain concentration gradients and how they relate to diffusion. And second, what is the correct unit for blood pressure? Go ahead and try to answer those. Hopefully you've done that, so let's see what the correct answers are. First, explain concentration gradients and how they relate to diffusion. Well, think back to Bio 137. We said a little bit in lecture, more in lab, but we saw that when there is a greater concentration of something in one area and a lesser concentration of something in another area, everything likes to move from an area of high concentration towards an area of lower concentration. So that process of moving from high to low concentration is diffusion. But we're going to learn today that this applies to more than just concentration. So keep this in mind. This exact process is going to come back today. Next, what's the correct unit for blood pressure? Well, the key term there is pressure. We said that every time that we talk about pressure in this course, the units are going to be the same. It's going to be mmHg, millimeters of mercury, and that's going to be the case today. So we're going to talk a little bit about physics, and I know that's a word that scares students pretty often, but just rest assured this is not going to be anything like the level of physics that you would find in a physics class. This is just not even the bare bones of physics. This is just introducing a couple of very basic concepts, nothing very deep at all. So when we talk about breathing, we're going to be talking a lot about pressure. It's going to be pressures of gases, pressures of air, basically. And we're going to mention several different types of pressure. And this is going to be the foundation for the physics that we're talking about. So first, let's learn about the different pressures that we're going to be talking about. The first is atmospheric pressure. This is the pressure of the atmosphere, and specifically, we're going to be talking about atmospheric pressure at sea level. If you go higher than sea level, pressure is a little bit lower. If you go lower than sea level, that doesn't necessarily mean underwater, just lower than sea level, then pressure is a little bit higher. So why is that, and what is atmospheric pressure? Well, when you go outside, if it's not raining, it's not snowing, it's not doing anything, when it's just a calm day, it seems like there's really nothing around you, but that's not true. We saw in the chemistry chapter that there's all kinds of stuff there in the atmosphere or in an empty room or whatever. There's things like oxygen and carbon dioxide and hydrogen and nitrogen and water vapor, all of that makes up the atmosphere. And the atmosphere is constantly pressing down against you. And if you go up higher, like up high in the mountains, well, now there's less atmosphere above you, so less atmosphere is pressing on you, and that's why there's a lower atmosphere the higher you go. And if you go down very, very low areas below sea level, well, now there's more atmosphere above you, so more atmosphere is pressing down on you, and it would be greater. So at sea level, the atmospheric pressure is 760 mmHg. That means when you go outside, even when you don't think that you're really feeling anything, there is actually 760 millimeters of mercury of pressure from the atmosphere pushing down on you. So that's one of the pressures we're going to be talking about is atmospheric pressure. And like I said, at sea level. Now, we are going to give some examples, and they are always going to use at sea level. Just keep in mind that if it's not at sea level, some of these numbers would be a little bit different, but all the processes would still be the same. Next is intrapulmonary pressure. So intra means inside of, and pulmonary is referring to your lungs. So the intrapulmonary pressure is the air pressure inside your lungs. Your lungs, like we saw in the previous lecture, mostly hollow because of all of those alveoli. Now, there are the branches of the bronchial tree, and there are the tissues that make up the walls of the alveoli and blood vessels, but in general, we can kind of think of the lungs as hollow, so they're filled with air. That air pressure inside is called the intrapulmonary pressure. And again, this pressure is always going to be in mmHg. And at the start and end of each inhale and exhale, the intrapulmonary pressure is going to be equal to atmospheric pressure. As we are breathing, as we're inhaling and exhaling, the intrapulmonary pressure is going to rise and fall with each breath that we take. But at the end of each breath, after we finish inhaling, and again, after we finish exhaling, the intrapulmonary pressure is going to be equal to atmospheric pressure. The third pressure we're going to talk about is IntraPlural pressure. Remember the pleura? Those membranes, that double layer membrane around the lungs? Well, we said one layer lies directly on the surface of the lung, the visceral pleura, and the outer layer, the parietal pleura, we said lie against the thoracic wall, the wall of the rib cage, and the space in between was where we found pleural fluid. Well, where that pleural fluid is, so in between the visceral and parietal pleural layers, that is the intrapleural pressure. And it is always just slightly less than intrapulmonary pressure. What that means is if intrapulmonary pressure is 760, well, the intrapleural pressure would be somewhere around 756. So it's just slightly less than the intrapulmonary pressure. And the reasons that it is slightly less, like what actually causes it to be slightly less, is two factors to do with the lungs. The lungs are kind of like a rubber band. They like to recoil. When they're stretched, they will snap back. So they're constantly trying to snap back to as small as they can possibly be. And surface tension. We said that the lungs are moist, and we talked about surface tension in the previous lecture. Well, that surface tension also is trying to shrink the lungs down. Because the lungs are constantly trying to shrink for both of these reasons, that creates a little bit of a vacuum. And that is what the intrapleural pressure is. It's the result of that vacuum. So it's always just a little bit less than intrapulmonary pressure. Now, if we compare intrapleural pressure and intrapulmonary pressure, the difference in the two is called the transpulmonary pressure. The transpulmonary pressure. We find that by taking the intrapulmonary pressure and the intrapleural pressure and finding the difference. So the way you find it is intrapleural minus intrapulmonary. Intrapleural minus intrapulmonary, and that will give you a negative number. In the example that we gave with the intrapulmonary pressure being 760 and the intrapleural pressure being about 756, well, that means that the transpulmonary pressure is negative 4 millimeters of mercury, negative 4 mmHg. The greater that number, and I don't mean closer to zero, I mean ignore the negative sign, the greater the magnitude of that number. So negative 4 or negative 6 is greater, or negative 8 is even greater. Well, that determines the size of the lungs. Negative 4 stretches on the lungs a little bit. Negative 6 would stretch on the lungs a little bit more and make them bigger. Negative 8 would stretch on the lungs even more and make them even bigger. So the transpulmonary pressure determines the size of the lungs by stretching on them. Now, before we go on and start talking about how we breathe, let's talk about a couple of things that could go wrong with relation to those pressures. First, there is something called pneumothorax. Pneumothorax, the literal translation is air in the chest, but pneumothorax is when you have a hole in the wall of the chest. And if you have a hole in the wall of the chest, now that transpulmonary pressure is going to go away, because suddenly the intrapulmonary pressure is, still equal to atmospheric pressure. The intrapleural pressure is now also going to be equal to atmospheric pressure because it's exposed. It's exposed to atmospheric pressure. And if the intrapleural and intrapulmonary pressures are equal, what does that do to transpulmonary pressure? It makes it 0. So now we're not stretching the lungs anymore. We're not pulling on them. What happens? Well, we said that recoil and surface tension is the lungs trying to shrink down to their smallest possible size. If we are not stretching on the lungs, they will shrink down to their smallest possible size. We say they will collapse. So pneumothorax, air in the wall of the chest, causes a collapsed lung. But we don't call it a collapsed lung. We call it atelectasis. Atelectasis is a collapsed lung, and atelectasis results from pneumothorax. Okay, so here come the physics that we're going to be responsible for knowing. The first thing that we're going to talk about is something called Boyle's Law. Boyle's Law says that pressure of something and volume of something are inversely related. They are inversely related. And really, all that means is when one goes up, the other goes down. So let's see how that relates to what we're talking about. Boyle's Law, really the way that it's written out is P1V1 equals P2V2. Pressure 1, volume 1 multiplied together equals pressure 2, volume 2 multiplied together. We are not using it that way. So don't worry about it. You don't need to know that for our class. What I do want you to know is that as volume increases, pressure decreases, and vice versa. We could also say as volume decreases, pressure increases. The takeaway is whatever volume does, pressure does the opposite. So let's see how that relates. Here we have a container with some sort of gas inside of it. All right, so we have a volume, whatever the size of this container is. And then we have stuff inside of it, shown here as these little black balls, but this is just some sort of gas or some sort of liquid or whatever. So that's the pressure. Well, this device, we're going to push down on it. And this little part right here, the top of the container, is going to move downward. That's what we see over here. What has happened to the volume? The volume has gotten smaller when we pushed the top down. And as we push the top down and the volume gets smaller, this gas inside is pressed more tightly together. It is under greater pressure. Over here in part 1, we have a large volume and a small pressure. Over here, the volume is much smaller and the pressure is much higher. So as volume decreases, pressure increases. If we were to raise the top back up, well, the volume has gotten bigger and the pressure has dropped. So whatever whatever volume does, pressure does the opposite. The importance of learning the pressure-volume relationship in this chapter is because of the next part. When there are two different pressures and an available pathway, the result is movement. Because, as we saw in the not really attendance questions, when there was a concentration gradient, when there was greater concentration of something in one area than the other, everything liked to move down its concentration gradient. Everything liked to move from high concentration towards low concentration. Well, now we're going to say the exact same thing, except we're going to change the word concentration to the word pressure. Everything likes to move from an area of high pressure to low pressure. Everything likes to move down its pressure gradient. So let's relate that back to our little diagram here. When we looked at it the first time, we said we had a container and we pushed down on the top, and now the same container has a smaller volume and a greater pressure. Let's pretend these are two different containers now. Let's say this container is bigger, it has a greater volume, and the pressure inside is pretty low. This second container has a smaller volume, and the pressure inside is pretty high. So we have two separate containers. The pressure inside them is different. Low pressure on the left, high pressure on the right. Now, let's put a pathway in between them. There's a low pressure on the left, high pressure on the right, and an available pathway. What do you think is going to happen? We have two different pressures with an available pathway. We say that it results in movement. And when we talked about concentration being the same as pressure now, what will happen? Well, there's going to be movement. And the movement is going to go from an area of high pressure towards an area of low pressure. So stuff on the right is going to flow through the pathway towards the left. Things are going to move from high pressure over towards low pressure. Now the question is, how long will that movement occur? It will keep moving until there is equilibrium, until the pressure on the left and the pressure on the right are equal to each other, just like we saw with concentration. Make sure everything up to this point makes sense. Listen to it a few times if it doesn't, because now we're going to take those physics that we just learned. See, I told you the physics weren't going to be very deep. That's all the physics that we're going to learn for now. We're going to take that physics that we just learned and apply it to how we breathe. So here we see some lungs inside of a chest. And this red line here is the diaphragm. So this kind of gray line on each side, this is the rib cage. This is the chest cavity. This is the diaphragm. Inside here we have the lungs. So inside here, inside the lungs, this is the intrapulmonary space. Outside the lungs, but inside the rib cage, this is the intrapleural space. Now out here, we see this is the atmosphere. This is 760. I have not written the units because it's going to get kind of crowded in a little bit, but just know we should write 760 mmHg, millimeters of mercury. This is atmospheric pressure at sea level. Now what we're going to do is look at how breathing occurs. So right now we are, let's say, at the end of an exhale. We are going to say no air is moving in or out of the lungs. We have just finished exhaling and we have not yet started inhaling. So pressure, atmospheric pressure is 760. Pressure inside the lungs is also 760 mmHg. So intrapulmonary pressure is 760 mmHg. The space in the intrapleural cavity is 756 mmHg. Remember, it's just slightly less than the pressure inside the lungs. It's stretching on the lungs a little bit. It's keeping them inflated. Now, we are going to look at how we breathe. We're going to look at how we inhale, and then we're going to look at how we exhale. We're going to be talking about some muscles. When we are just breathing normally, we say when we are experiencing normal, quiet breathing, or eupnea, normal, quiet breathing, or eupnea, we're going to use some muscles that are in between each of our ribs, called the external intercostals, and we're going to use the diaphragm. So external intercostals and diaphragm are the muscles involved in normal quiet breathing. Let's now look at everything that happens when we inhale. First, we're going to contract our external intercostals, and our rib cage is going to move upward and outward. That's what these arrows represent. We contract the external intercostals and the ribs move upward and outward. We also contract the diaphragm and it moves downward or inferiorly. When we do that, the ribs move up and out, the diaphragm moves down. Think about this area right here, the intrapleural space. What's going to happen to it? Is it going to get bigger or smaller if the ribs move up and out and the diaphragm moves down? Well, the intrapleural space is going to get bigger. We say the volume of the intrapleural space increases. Well, if the volume increases, what's going to happen to the pressure in the intrapleural space? It's going to drop. It's going to decrease. So if it decreases, it doesn't matter how much it decreases. It's just going to decrease some. So I change the 756 to 750. Are we stretching the lungs more or are we stretching the lungs less? Well, think about what transpulmonary pressure did. Remember, transpulmonary pressure is what actually stretches the lungs. Well, it went from 756, it had a difference of 4, to 750. Now it has a difference of 10. So it's going to be stretching on the lungs more. What's going to happen? The lungs are going to get stretched in all directions, meaning the lungs are going to get bigger. So if the lungs get bigger, now we're talking about the intrapulmonary space. If we're stretching the lungs and making them bigger, the intrapulmonary space increases. The volume goes up. The volume of the lungs themselves increases. And if the volume increases, what's going to happen to the pressure? decrease. The pressure inside the lungs, the intrapulmonary pressure, is going to decrease because the volume increased. Doesn't matter how much it decreases. It just needs to drop a little bit. I showed it dropping to 752. Well, as soon as this drops below atmospheric pressure, which is exactly what it did, there's going to be something that happens. The pressure in the lungs has dropped below atmospheric pressure. There is a difference in pressure. Also, there is an available pathway. Remember, the inside of the lungs are outside your body. Well, we said if you lean your head back and open your mouth, there's really just an open pathway between the atmosphere and the inside of your lungs. Yeah, there's an epiglottis there, but it's open unless you're swallowing. So what do we think is going to happen? Well, there's high pressure out here in the atmosphere. There's lower pressure in here in your lungs, and there is an available pathway. That means there will be movement, and air begins to rush into your face, down your throat, and into your lungs. You've just inhaled. Air is moving into your lungs because of pressure differences. And air continues to rush into your lungs until what? Until there is equilibrium and we're right back where we started. Now we are at the end of an inhale. Atmospheric pressure is still 760. The lungs have risen back up to 760 of the intrapulmonary pressure. IntraPlural pressure now slightly less, so 756 again. That means that the transpulmonary pressure is right back to about -4. Watch that segment a few times until you can understand the mechanics of inhaling. Because next we are about to look at exhaling. So, when we go to exhale, we are going to relax the external intercostals and the ribs move inward and downward. We are going to relax the diaphragm, which is going to move upward. The ribs moved inward and downward. The diaphragm moved upward because the intercostals relaxed and the diaphragm relaxed. Now, as a result of that, what's going to happen to the intrapleural space? Well, the volume is going to decrease. And if the volume decreases, the pressure in the intrapleural space increases. It's not going to increase a lot. It doesn't need to. I'm showing it increase from 756 to now 758. So what does that mean? It means that transpulmonary pressure pulling on the lungs has changed from 4 to 2. We are not stretching the lungs as much. Well, what does that mean happens? Because of that recoil, the lungs are going to snap back. They're going to get smaller, and the volume of the intrapulmonary space decreases. If the volume decreases, what happens? The pressure in the intrapulmonary space inside the lungs increases. How much does it increase? Just a little bit, but it doesn't have to increase a lot. We're going to say it goes up to 765. And if it goes up to 765, it's now above atmospheric pressure. There's still this available pathway, But what's going to happen? Well, now pressure in the lungs is greater than pressure in the atmosphere. So air rushes out of your lungs, out of your face, and into the atmosphere. We have now just exhaled. And we continue to exhale. Air continues to leave our lungs until what? Until equilibrium is reached again, and then we are right back to the very first picture that we had, getting ready to inhale again. So this is the way your book shows everything that we just drew. This is showing what muscles are involved and what happens to the space inside the chest. But it's all about volume and pressure changes. And additionally, let's talk about what muscles not just are involved, but what we're doing with them. Well, when we are inspiring, when we are inhaling, we are contracting the muscles, the external intercostals and the diaphragm. When we are expiring or exhaling, we are relaxing those same muscles, the external intercostals and the diaphragm. So inspiring, inhaling is active. Exhaling is passive. Inhaling uses energy because we're contracting muscles. Exhaling does not use energy because we're relaxing muscles. But there are some other things that could happen. So let's take a look at those. There's something called forced expiration, like when you're blowing out a candle or blowing on someone's neck to scare them or something like that. If you play a musical instrument that requires you to blow air into it, all of that is called forced expiration. And in forced expiration, well, this uses a different set of muscles. It uses the internal intercostals and the abdominals. And remember, the quiet expiration, the eupnea expiration, that was passive. We were relaxing muscles. But forced expiration is active. It contracts the internal intercostals, it contracts the abdominal muscles to force air out. Now, lung compliance is something that plays a big role in the ability to inhale and exhale. Lung compliance is the ability of lungs to expand. We want lungs to be very pliable. We want them to expand easily and snap back, and then expand easily and snap back. Anything that interferes with lung compliance, smoking, COPD, things like that, anything that interferes with the lungs' ability to expand makes those volume changes difficult. And if the volume changes don't occur easily, then those pressure changes also don't occur easily. Let's talk a couple more disorders. First, asthma. Asthma is what happens when the walls of those small air tubes, like the very small bronchioles, become thickened. So the mucosal layer, which is generally pretty thin, allowing for a pretty large area of, remember, the open area of any hollow organ is called the lumen. So the lumen is pretty large and the mucosal wall is pretty thin. Well, I guess this is the submucosa. The mucosa itself doesn't really thicken that much. But in asthma, different triggers can cause that submucosal layer to get much thicker, resulting in a much smaller lumen, meaning that there's less room for air to move through there. Think about someone who has asthma that has a rescue inhaler. Well, rescue inhalers are generally something like a steroid. And steroids, what was one of the things we learned that steroids do? For example, when we were talking about cortisol back in the very first block of the semester, it reduced inflammation. Or if you inject someone with an epinephrine pen, that can also do it. Well, this thickening up is undone by something like steroids, and most asthma inhalers are steroids, something like albuterol. And the other disorder we will talk about is infant respiratory distress syndrome, or IRDS. This is something that it can happen to any baby, but it is much, much more common in preemies, the prematurely born babies. What happens in IRDS is when a baby is in the womb, it doesn't need to breathe. It's getting all of its oxygen and carbon dioxide exchange through mom. So other things are being developed first. But there's no reason for the baby's lungs to develop until very, very near the end of pregnancy because they're not needed. So when I'm talking about lung development, one of the things that I'm talking about are those type 2 cells. Remember, type 2 cells secrete surfactant, which decreases surface tension. Well, in babies that are born early, a lot of times they are born before those type 2 cells are fully developed. So they don't secrete surfactant, which means that the lungs have to fight against surface tension to inflate. Now, in an adult, it would be pretty difficult to inflate lungs with surface tension. You have to exert a lot of energy each time you take a breath. In a baby, that energy exertion is too much. So what happens is when the baby exhales, surface tension forms around the alveoli, and then the baby cannot inhale again. So that's one of the leading causes of death for premature babies. That's why almost always you will see premature babies immediately put on a ventilator that's actually blowing air into their lungs instead of relying on them to inhale on their own. All right, our last little bit of topic are lung volumes and capacities. This is something called a spirograph or a respirograph, and spirographs are measuring different lung volumes. Right in the middle, this very light blue area, we can see a small wave up and down, and then here's an up and down, up and down. This is normal, quiet breathing. This is the breathing that you don't think about when you're not paying attention and you're just breathing kind of on autopilot. We say that is normal, quiet breathing, or eupnea again. Well, the volume of air moved in normal, quiet inhale or normal, quiet exhale is called the tidal volume. And in the average healthy adult white male, it's about 500 milliliters. So inhale, 500 milliliters. Exhale, 500 milliliters. That's normal, quiet breathing, tidal volume inhale or tidal volume exhale, about 500 milliliters. Next, something called the inspiratory reserve volume. That's this kind of gray-purple area up at the top. Inspiratory reserve volume is air that you can forcefully inhale after a normal tidal inhale. What I mean by that is if we start here at an exhale and then we inhale our normal breath, we do not count that. That is tidal volume. But after a normal inhale, your lungs are not full. You can force yourself to inhale much more. Well, the volume that you can force yourself to inhale after a normal tidal volume inhale is the inspiratory reserve volume, and is about 3,100 milliliters of air. Next, the expiratory reserve volume, this dark blue area here. It's kind of the opposite of inspiratory reserve. Here you breathe normally, you exhale normally, you inhale normally, you exhale normally, but after the normal exhale, your lungs are not empty. You could force yourself to breathe out even more. Well, the volume of air that you can forcefully exhale after a normal tidal exhale, that is the expiratory reserve volume, and it's about 1,200 milliliters. So you breathe out normally, you don't count that. That's tidal. But you continue to force air out, that's the expiratory reserve volume. After you've breathed out as much air as you can possibly force yourself to breathe out, your lungs are not empty. They do not collapse on themselves. There's still quite a bit of air left in your lungs. That's called the residual volume. The residual volume is the air that remains in your lungs always. It is the air that remains in your lungs after expiring the expiratory reserve volume. That's the residual volume. Now, capacities are when we take some of those volumes and add them together. First, inspiratory capacity is tidal volume plus inspiratory reserve volume. Functional residual capacity is expiratory reserve volume plus residual volume. Vital capacity is all of the air that you can possibly move. It is inspiratory reserve volume plus tidal volume plus expiratory reserve volume. One way to kind of picture vital capacity is take as deep of a breath as you possibly can and hold it. Your lungs are as full as they can get. Now blow all of the air out that you can possibly breathe out until you can't breathe out anymore. The volume of air that you just blew out is the vital capacity. And lastly, total lung capacity is inspiratory reserve volume, tidal volume, expiratory reserve volume, and residual volume. It is all of the air that you can possibly breathe out plus all of the air that you cannot breathe out. And alveolar ventilation. So this is measuring some of those things that are going on in your lungs and how we use it for calculation. Well, first, there's one more thing that is not actually on this graph, and that's something called dead space or anatomical dead space. That means even though we talk about the lungs as though they are hollow, they're not really completely hollow. There are the walls of the alveoli, the walls of the capillaries, the walls of the bronchial tree. All of that takes up space inside the lungs, but it plays no role in being air itself. So dead space is the volume of the conducting zone, and it comes to about 1 milliliter per pound of body weight. So if we go back and we think about how much the lungs can hold, well, 1 milliliter per pound of body weight is actually not going to be calculated into that. Two terms here, minute ventilation, MV. Minute ventilation is found by breathing rate, how many breaths per minute, times tidal volume, how much air is moved per breath. Does this sound at all familiar? It should. This is the same kind of thing as cardiac output that we just talked about. Cardiac output is equal to heart rate times stroke volume. Well, now we're moving away from the heart, but we're looking at the lungs. Minute ventilation, how much air is moved per minute? It's found by how many breaths per minute times how much air is moved per breath. But really the more important or the better measure is something called alveolar ventilation rate. This is looking at how much air that you breathe in actually gets to the parts of the lungs involved in gas exchange, down deep into those alveoli. Well, AVR, alveolar ventilation rate, is equal to breathing rate times tidal volume minus dead space. Tidal volume minus dead space times breathing rate is alveolar ventilation rate, and that tells us how much air that you're breathing actually gets to the part of your lungs involved in gas exchange. And speaking of that, take a breath. We've gotten to the end of that lecture, and once we get to our next lecture, we will start looking at a little bit more of how do lungs work with those pressures? What are some other physics things related to those pressures? And how do we move gases around in the body? All right, take care, and I will talk to you next time.